Başlatıyorum sen.
Recording in progress.
Hi teacher. Today we're going to talk about the Concerency issues. We will examine the topic with 7 titles. The first title is multithreading. Multithreading has parallelism. And now we will look at the parallelism benefits. The first one is improved performance. Parallelism can significantly enhance the performance of applications by executing multiple tasks simultaneously, leading to faster execution times and increased throughput. The second one is resource utilization. By leveraging multiple threads, parallelism maximizes utilization of available hardware resources, such as CPU cores, reducing idle time and improving overall system efficiency. The third one is scalability. Parallelism enables applications to scale effectively by distributing workload across multiple threads, allowing them to handle larger data sets and more complex tasks without a proportional increase in execution time. And now we will learn how will we manage the thread. Our step 1 is thread creation. Creating threads efficiently is crucial for performance, as excessive thread creation can lead to overhead and resource contention, while too few threads may underutilize available resources. And step 2 is thread scheduling. Effective thread scheduling ensures that threads are executed in a balanced manner, preventing any single thread from monopolizing resources and allowing for fair distribution of work. And last one is thread termination. Proper thread termination is essential to avoid resource lags, such as memory and file handles, which can lead to system instability and performance degradation. Shared resources. Memory sharing. Shared memory allows multiple threads to access and modify the same data, enabling efficient communication and coordination between threads, but it also introduces the risk of race conditions and synchronization issues. Resource contention. Contention occurs when multiple threads compete for access to the same resource, leading to delays and reduced performance. Proper synchronization mechanisms are needed to manage contention effectively. Locking mechanisms. Locks, such as mutexes and semaphores, are used to control access to shared resources, preventing multiple threads from modifying the same data simultaneously and ensuring data consistency. The performance gains. The first one is reduced latency. Parallelism can significantly reduce the latency of critical operations by executing them concurrently, leading to faster response times and improved user experience. Increased throughput. By processing multiple tasks simultaneously, parallelism increases the throughput of applications, allowing them to handle more requests per unit of time and improving overall system performance. Load balancing. Effective load balancing. You can mute your microphone, Giray. There are a lot of sounds. Load balancing.
It's not my microphone.
Effective load balancing ensures that work is evenly distributed across threads, preventing bottlenecks and maximizing the utilization of available resources, thereby enhancing performance and scalability. Parallel algorithms. Designing algorithms that can be executed in parallel can lead to significant performance gains, as these algorithms can leverage multiple threads to solve complex problems more efficiently. And our next topic will be the race condition, and my friend Ibrahim will tell you. Thanks for listening to me.
Okay, thank you, my friend. So, what is the race condition? A race condition occurs when the program result depends on the timing or interleaving of concurrent operations. So when two specific tasks want to achieve the same result, for instance, when we have one bank account and it has a wallet, and two people want to access it at the same time and withdraw the same amount. So when two people want to extract the same amount, this is a race condition because one of them is going to be first and the operation will happen at the same time. So at the end, we will have a thing like negative balance, for instance. It causes such weird situations. And we have another race condition example, lost update. Two threads execute counter plus plus on a shared variable at the same time. The increment is not atomic. Each thread reads the value as one, then writes it back. If both threads read the same old value or one update is lost, so the final counter value is smaller than expected. And then we have deadlocks. Kaufman conditions for deadlock. Mutual exclusion. Resources cannot be shared. Only one process can use the resource at any given time. And we have hold and wait. A process holding at least one resource is waiting to acquire additional resources held by other processes. Deadlock example with two processes. We have process A and B. Both processes hold one resource and request the other, leading to a deadlock state. Wanting to access the same resource, so it deadlocks the states. Simply, resource allocation graph visualizes the deadlock using nodes for processors and resources and edges for resource requests. So handling strategies for deadlocks, we have deadlock prevention. Design systems to avoid possibility of deadlock by ensuring at least one of Kaufman conditions cannot hold. And we have deadlock avoidance, ensures that system never enters an unsafe state by carefully managing resource allocation. And we have deadlock detection techniques. Wait for graph technique constructs a graph to detect cycles which indicate a deadlock. Processes are nodes and edges represent resource requests. And we have prevention techniques. We have three prevention techniques: prioritizing locks, avoiding cycles, and system-wide consistency. Assign a global order to all locks to prevent the circular wait conditions, ensuring deadlock avoidance by enforcing a consistent locking hierarchy. And second one is avoiding cycles by enforcing a total order among locks. The system ensures that no process can create a deadlock cycle, as it will always request locks in a non-cyclic sequence. And the third one is system-wide consistency. This technique requires coordination across the entire system, making it suitable for environments where lock ordering is feasible and manageable. Avoiding hold and wait, releasing before the request, and we ensure that a process releases all locks before attempting to acquire new ones, eliminating the hold and wait condition that can lead to deadlocks. And dynamic allocation, allocate resources dynamically and only when needed, rather than holding multiple locks simultaneously to reduce the likelihood of deadlock. Try locks, non-blocking attempt, which is attempting to acquire a lock without blocking if it is not immediately available, allowing the process to continue execution and retry later. Safe states, we have Banker's algorithm here. Determine a safe state where all processes can complete without reaching an unsafe state, ensuring deadlock avoidance through resource allocation planning. And we have modern concurrency. Three steps of importance of multi-threading and concurrency issues. Enhanced performance is step one. Multi-threading allows efficient utilization of multi-core processors, significantly improving application performance and responsiveness. Resource sharing is step two. Threads with the same process can share memory and resources, reducing overhead and improving efficiency compared to process-based parallelism. And step three is responsiveness. Multi-threading enables applications to remain responsive by performing long-running tasks in separate threads without freezing the user interface. Why race conditions and deadlocks are dangerous? Unpredictable behavior, system instability, and security vulnerabilities. I would like to give one more example for this situation where a race condition happened recently in a big tech company in Amazon Web Services. For instance, in their situation, a race condition happened and it made the access to DNS records of the it was a table that was holding the information of the web apps, I think, not DNS records. It was inaccessible. The DNS was inaccessible, and they had a race condition. They wanted to update the previous records, so they deleted the previous ones. So while trying to update, they deleted the previous one. So it was a race condition. Even it happens in a very big tech company, a multi-billion-dollar company. Race conditions led to inconsistent and unpredictable outcomes, making software behavior difficult to debug and maintain, which I gave an example a moment ago. Deadlocks can cause systems to freeze, requiring manual intervention or restarts, leading to poor user experience and potential data loss, which happened, as I said earlier. Concurrency bugs can be exploited to create security vulnerabilities, exposing sensitive data or allowing unauthorized access. Thank you for listening.
Conclusion and key takeaways. Race conditions and deadlocks are fundamental risks in multi-thread systems. Correct synchronization disciplines and consistent log ordering are essential to avoid them. Modern abstractions help reduce low-level bugs, but careful design and testing are still necessary. Concurrency safety should be treated as a first-class design goal, not an afterthought. Background process, threads, and shared memory. Processes are independent instances of programs with their own memory space, resource, and execution context. Threads are lightweight execution units within a process, sharing the process memory space and resource. Shared memory. Shared memory allows multiple threads to access and modify the same data, enabling efficient communication and coordinations. Critical sections and synchronization primitives. Critical sections are code segments where shared resources are accessed, requiring synchronization to prevent concurrency issues. Mutexes ensure that only one thread can enter a critical section at a time, preventing race conditions. Spin logs are busy wait logs that repeatedly check for availability, useful in a low latency systems, but can waste CPU cycles. Semaphores are signaling mechanism that control access to shared resources, supporting more complex synchronization scenarios. Concurrency problems overview. Race conditions occur when the outcome of a program depends on the sequence of execution of concurrent threads. Deadlocks happen when two or more threads are waiting indefinitely for each other to release resources, causing a system halt. Lealock is similar to deadlock, where threads repeatedly change their state without making progress, appearing active but unproductive. Starvation occurs when a thread is perpetually denied necessary resources, preventing it from making progress despite being ready to execute. Thank you for listening us. Thank you, my friends.
Recording stopped.